Hello again, and welcome to the first of two lectures on the so-called conic sections. In this lecture and the following lecture, we'll talk about circles, parabolas, ellipses, and hyperbolas. Needless to say, there are lots of applications of these concepts, both in pre-calculus and especially in calculus. In calculus courses, one uses parabolas and ellipses and things like that all the time. This lecture, I'd like to focus on circles and parabolas, and then the following lecture we'll talk about ellipses and hyperbolas. And let me just add that in the final lecture of this series, I'll take a brief look at GPS devices, which will involve circles once again. So what do we mean by a conic section? Imagine the following. Imagine two cones that are hooked together at their vertices. This is often called a double-napped cone. And imagine a plane intersecting those two cones that are glued together. It can intersect in many ways. It might intersect perpendicular to the axes, and you would get a circle as the figure of intersection. Or it might intersect at a slight angle, and that'll generate an ellipse. It could intersect at much more of an angle, and you'll get a parabola. And then the hyperbola is an intersection perpendicular to the two cones like this, a vertical intersection. And then you could also get some so-called uninteresting intersections. It might cut right across the vertex, and the intersection is a point. It could intersect in a line or in a pair of lines. We won't worry about those kinds of intersections. We're going to be talking about circles, parabolas, ellipses, and hyperbolas. So what's a circle? Well, we've been dealing with circles already. Everybody's familiar with a circle. Here's the technical definition. A circle is the set of all points, the locus of points, x, y, in the plane that are equidistant from a fixed point hk. That's the center of the circle. The distance between the center and any point on the circle is called r, the radius. And knowing that definition as a set of points satisfying that criteria, you have the standard form of a circle that's very familiar to us, I think. X minus h quantity squared plus y minus k squared equals r squared. And in the happy circumstance that the circle has its center at the origin, then the equation simplifies to x squared plus y squared equals r squared. A very familiar equation. Here's a picture of our circle with center hk and radius r, and the points x, y are distance r from the center. So let's play with some circles for a moment. Let's derive some equations of circles and get comfortable with this definition. Here's my first example. The point 1, 4 is on a circle, and suppose you also know the center is minus 2, minus 3. Can you find the standard form of the equation of that circle? So we're given the center, minus 2, minus 3, and we're given a single point on the circle. What's the equation of this circle? Well, one way to do it is first find the radius, which is the distance between that point and the center. And that radius would be the difference in the x values squared, so 1 minus a minus 2 quantity squared, plus 4 minus a minus 3 quantity squared, all square rooted. That'll give the radius, and that simplifies to 3 squared plus 7 squared, or 58. So the radius is the square root of 58. Not a real pleasant number, but there it is. And now we take the equation, x minus h squared plus y minus k squared equals r squared, and plug in all these characters. H, you remember, is the x-coordinate of the center, minus 2. K is the y-coordinate, minus 3. And so you have x minus a minus 2 squared plus y minus a minus 3 squared equal to the radius squared, which is square root of 58 squared. And so the square root sign disappears, and you're left with x plus 2, minus makes plus. So x plus 2 squared plus y plus 3 squared equals 58. There's your final equation of that circle. Okay, here's a picture of it. There's the center at -2, -3. The point 1, 4 is indicated on the circle, and all the other points are the same distance away from the center. So let's analyze another equation, and we'll discover that this is also a circle, but it's sure not written in the standard form. Let's look at the equation x squared minus 6x plus y squared minus 2y plus 6 equals 0. This kind of looks like a polynomial, doesn't it? It's got some x squared and x terms, but it also has some y squared and y terms. It's kind of, you might say, a polynomial in x and in y. And it turns out this is actually the equation of a circle. How are we going to show that? Well, remember how we used to complete the square? We're going to use that skill again. So we start off with our equation, x squared minus 6x plus y squared minus 2y plus 6 equals 0, and we complete the square both for the x terms and for the y terms. So write it like this, x squared minus 6x plus something. What should I put in there so that x squared minus 6x plus that new value is a perfect square? Well, remember the rule, you take the 6, or the minus 6, divide it by 2, and square it. So it'd be 3 squared, or 9. So 9 is the missing term there. Now look at the y, folks. Y squared minus 2y plus somebody. Well, that's pretty easy to see. You would add 1. That's 2 divided by 2 squared. Now, what about that 6 that was in the original equation? First of all, move it to the other side, so it becomes minus 6. And we changed the problem, didn't we? We added a 9, and then we added a 1 to complete the squares. So add the 9 and the 1 on the other side as well. And we're left with the following. X minus 3 quantity squared. We made it a perfect square, didn't we? Y minus 1 quantity squared. And then all the little numbers on the right-hand side add up to 4. So there's our standard equation of the circle. We started off with that funny polynomial type equation, completed the square, and now we discover, oh, that's a circle. What's the center and what's the radius? Well, the center is 3, 1, and the radius is 2. Remember, it's r squared on the other side. The square root of 4 is 2. Here's a picture of that circle. I've indicated the center at 3, 1. And because the radius is 2, you can actually draw some more points on this very conveniently. The point 5, 1 is on the circle because that's 2 units from the center. So is the point 1, 1, and the point 3, 3, and the point 3 minus 1. So you see that we can draw some more points on the circle because we know its center and we know its radius. All right, why don't you be the teacher for a moment? Suppose a student were to ask you the following question. Teacher, how many ways can 2 circles intersect each other? You have 2 circles. How can they intersect each other, and how many points of intersection could there be? Well, let's think about it. First of all, the circles might be disjoint. They might be far away from each other, and there's no point of intersection at all. Or they could be tangent to each other. The circles just kiss each other at one point. Or, perhaps more common, the circles intersect at 2 points. And you can sort of think of a circle on top of another circle. And then kind of an extreme case, the circles could be identical, be the same circle, and then they intersect everywhere. And this is kind of a good question, I think, that a student would ask, because I mentioned that we'll talk about GPS devices in the final lecture of this series. The discussion will involve intersecting some circles. And so it's important to realize, I think, the fact that they possibly can intersect in 2 points. All right. Let me remind you of just point out some things about circles. First of all, circles are a special case of what we call ellipses. And ellipses we'll talk about next lecture. Ellipses are sort of more elongated. And we also defined a circle as a locus of points, or as a set of points satisfying a certain property. Well, that technique of dealing with a set of points satisfying a certain property is the same way we're going to define parabolas, ellipses, and hyperbolas. So it's kind of a common technique. And notice also in those examples we did, how important it is to know how to complete the square. Pre-calculus, completing the square is an important skill, and that skill carries through to a calculus course. So let's move on to parabolas. We're familiar with, say, y equals x squared, one of our favorite curves, the parabola opening upwards. Well, we're going to dig a bit deeper now into the world of parabolas. We'll talk about their technical definition as a locus of points, as a set of points satisfying a certain property. We'll derive some equations for parabolas. They'll look a little unusual. We'll see some pictures, and then we'll work with those equations. So here we go. Here's the official definition of a parabola. A parabola is the set of points x, y in the plane that are equidistant from a fixed line, and that line is called the directrix, and a fixed point called the focus. And that focus is not on the directrix. So it's equidistant from a line and a focus, and a single point focus. Here's a picture of what I'm talking about. There is a focus, a single point, and down below you see a horizontal directrix, and a point xy is on that curve if the following is true. The distance from xy over to the focus, which is indicated by d sub 1, is the same as the distance from xy down to that directrix. That would be the perpendicular down to the directrix. Those distances are the same, and that generates this parabola, and in this case, it's opening upwards. Now, there's some more words here. The midpoint between the focus and the directrix is called the vertex, and that's indicated on the graph there. And then the line passing through the focus and the vertex is called the axis of the parabola. Okay, so, and that also is indicated. There's the axis of the parabola. So, with this definition of a parabola as a locus of points, you can derive the equations of parabolas. And that derivation's not very pleasant, and I don't think I'll do it today. But here's the resulting set of equations for parabolas. Okay, there are really, in a sense, two kinds of equations. The first kind of equation talks about parabolas that either open upwards or open downwards. And then the second group are parabolas that open to the left or to the right. So let's dig in. If you have a vertical axis, then the parabola either opens upwards or downwards. And the standard equation of that parabola with vertex hk is the following. X minus h quantity squared equals 4p y minus k, 4p times y minus k, where p is not equal to 0, of course. And if you have a horizontal axis, if the parabola is opening to the left or the right, then the equation is slightly modified. It's y minus k squared equals 4p x minus h. And of course, again, p is not 0. Okay. Kind of complicated looking equations, I admit it. Let me show you some pictures of how these equations work. Here's a picture of a parabola opening upwards. And its equation is x minus h squared equals 4p y minus k. And here's the case where p is greater than 0. And p is the distance between the vertex and the focus. So you see it indicated there, a positive number p. If the vertex is at hk, then the focus would be p units upwards, so it would be at h comma k plus p. You add p to the y coordinate. Notice that the directrix is equation y equals k minus p, because you're below the vertex. And then you could have a parabola opening downwards. And the only difference now is p is negative. And if p is negative, everything kind of gets reversed here. The vertex, again, is at hk, and the focus now is still h comma k plus p. But remember, p is negative. So when you say k plus p, you're going downwards. And again, the directrix is k minus p. And then you can have parabolas that open to the left and to the right. Here's one that opens to the right, and its equation is y minus k quantity squared equals 4p x minus h. P is greater than 0 when you open to the right, and look how it works. There's the vertex, hk, and there's the focus, p units away, and it's to the right because p is positive, and that focus is at h plus p comma k. And again, the directrix is over there on the other side. And finally, the fourth kind of parabola would be opening the other direction. Same equation, but p less than 0, and the focus is now on the other side of the vertex. Okay, so kind of complicated. I admit that, kind of complicated equations. Let's work with them for a bit. Let's do some examples, pin things down. Let's find the standard form of the equation of the parabola that has a fixed vertex and a fixed focus. Let's make the vertex the origin, and that's always nice when the vertex is the origin. And let's make the focus, say, 0, 4. So if the vertex is the origin down here and the focus is up higher at 0, 4, this parabola is opening upwards, isn't it? And in fact, I know P is 4 because that's the distance between the vertex and the focus. All right, let's get to work. The general equation for a parabola opening upwards is x minus h quantity squared equals 4p y minus k. And in particular, p is going to be positive, but the center, hk, is really 0, 0. So that compactifies everything, and our equation is x squared equals 4py. Pretty nice. We know what p is. It's 4. We've got the whole thing. X squared equals 4 times 4y, or 16y. If you want to write it in a more standard form, y is 1/16 x squared. That's our parabola. Here's a picture of it. There's the vertex at 0, 0, and there's the focus at 0, 4, and every point on that parabola is equidistant from the focus and the directrix. Bonus question. What's the equation of the directrix in this example? Well, if the focus is 4 units above, the directrix is 4 units below, so it must be y equals minus 4. Right. Let's do another example. How about the following parabola? See if you like this one. Let's find the standard form, and suppose the vertex is at 1, 0, and the focus is now at 2, 0. So the vertex is here. It's not at the origin anymore. And the focus is to the right, 1 unit to the right. So P is going to be 1 here in this case. Let's do it. Okay, what do we have? Because this is going to be opening to the right, we're going to use that second formula, y minus k quantity squared equals 4p x minus h. What's the center hk? H is 1 and k is 0. So we know some of the characters in that equation. What about p? Well, p was 2 minus 1, the distance from the focus to the vertex, so p is 1. I know everything. Here's the equation. Y minus 0 quantity squared equals 4 times p, 4 times 1 times x minus h, and h is 1, so it's x minus 1. Simplify, y squared equals 4 times the quantity, x minus 1. That's the standard form of this parabola. Here's a picture of it. Interesting looking parabola. It opens to the right. There's the vertex at 1, 0, and we've also indicated the focus at 2, 0. What's the directrix here? Well, it's on the other side. It's the y-axis, isn't it? It's the line x equals 0. It's 1 unit to the other side. Okay. Let's do some applications. Go back to that picture and imagine that parabola is rotated about its axis. It's rotated about its axis, generating a three-dimensional object. And that's called a paraboloid. And you can think of it as a parabolic reflector, or if you look at a flashlight, look down at a flashlight, don't have it on, of course, you'll see that the shape of a flashlight kind of looks like the figure I'm describing. And there's a reason for that. These paraboloids, these parabolas that have been rotated around to form a three-dimensional object, have a certain reflective property. And it says the following, that any rays coming in parallel to the axis are always reflected to the focus. So everything coming in from space with your satellite dish all get sent to the focus of the satellite dish. And that's why you can capture a lot of information and then focus it down to a single point. Or in the opposite way, if you have a flashlight or a headlight on your car, all the light coming out of the focus bounces off the parabolic reflector and goes out into the front. So it goes both ways. So they're kind of neat, this property of reflecting things. And you can prove that in a calculus course, for instance. It turns out that historically, they say that Archimedes actually used this reflective property of parabolas to concentrate the sun's rays on some attacking Roman ships. So Archimedes knew about this reflective property a long time ago. So here's a specific example of this reflective property. Suppose we had the following setup. We have an automobile headlight. So you can imagine what that in essence might look like. It's a piece of a parabola, and then it's rotated to produce a three-dimensional object. And that's going to be our headlight. And suppose the filament of the light itself is 1.5 inches from the vertex of the parabola. Here's a picture of what I'm talking about. The filament, and then you see the back of the headlight there. It's probably going to be metallic, so it'll reflect very well. And then light comes off that filament, hits the parabolic part, and then shoots off straight ahead. So what's the equation of our headlight? That's the question I'd like to ask. What's the equation for the cross-section of our reflector? Well, this won't be too hard. I think we can sort of set it up. Why don't we assume that the vertex is at the origin? And that'll make things a lot simpler. So now the equation, because it's opening to the right and the vertex is at the origin, it's y squared equals 4px, and p is going to be positive. And what's the value of p? Well, remember, the vertex and the focus are 1.5 inches apart, or 3/2. That's the p value. So p is 3/2. Plug that in, and we get y squared equals 4 times 3/2 x, and that simplifies to 6x. And so here's your equation of a cross-section of a typical headlight. It's 1/6 y squared equals x. Kind of nice, kind of a simple application. Okay, let's move on to a little more interesting problem. Suppose you're given the following equation. I'm going to give you an equation. What is it? What is it? Is it a circle? Is it a paraboloid? Or next lecture, will it be an ellipse or a hyperbola, whatever those are? Well, let's find out. Here's the equation. Y squared plus 6y plus 8x plus 25 equals 0. I want to analyze that equation. We're going to rewrite it, and we're going to use our skill of completing the square. All right. Notice in this equation that y occurs to the second power, but x only occurs to the first power. So I don't think this is going to be a circle. I'd have to have x squared to have a circle probably. So let's complete the square, but just for the y portion. So it's y squared plus 6y plus something. Y squared plus 6y, half of 6 is 3, 3 squared is 9. So it's y squared plus 6y plus 9. Then I have the 8x. Now that 25 in the original equation, move it to the other side. And we changed the equation slightly because we added 9 to complete the square, so add a 9 to the other side as well. And so what do we have? We have y plus 3 quantity squared equals minus 16. That's minus 25 plus 9. And that 8x, I'm going to motor that over to the other side as well. So it's minus 16 minus 8x. Now it's beginning to look like the standard form of a parabola, isn't it? we have to do some more massaging. Remember that equation had a 4 in it, didn't it? That general equation. So we're going to do some factoring here. First, factor out minus 8 out of the right-hand side, and you get minus 8 times x plus 2. And now do another factorization. Take out the 4, okay, because we need a 4. So now it's y plus 3 squared equals 4 times minus 2 times the quantity x plus 2. That's a standard equation of a parabola. That's a standard equation. Let's read off the information of this standard equation. What does this tell us about the shape of the parabola? Who's the vertex? Who's the focus? Who's the directrix, etc., etc.? Here we go. Well, what's the p-value? That's that little minus 2. So p is minus 2 here. What's the vertex? Well, that's the hk, and that's minus 2 minus 3, because it's x plus 2, which is really x minus a minus 2. So it's minus 2 minus 3. Well, what about the focus? Think about this a moment. If the vertex is at minus 2 minus 3, then where will the focus be? Well, p is negative. So we'll go to the left 2 more units, won't we? We'll go from minus 2 to minus 4. So the focus is at minus 4 comma minus 3. And what about the directrix? Well, it'll go 2 units the other way. So its equation is x equals 0. Here's a picture of that. Notice that it's opening to the left. The focus is at minus 4 minus 3. The vertex at minus 2 minus 3. Interesting looking graph, isn't it? Okay. Here's another bonus question today. You want to verify that you got this picture correct with your graphing calculator. How could you graph this? Look at the equation. Y plus 3 quantity squared equals 4 times minus 2 times x plus 2. Is that the equation of a function? Is that a function? Well, does the picture satisfy the vertical line test? No, this is not a function. And graphing calculators generally require that you're graphing functions. When you feed in an equation to graph in a calculator, it's y equals blah, 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 blah. Well, we're in trouble here. We've got y squared. What could you do? Well, you can break this into 2 pieces, the upper part and the lower part of this parabola. So let me show you how you do that. Take the y plus 3 squared equal, and I'll multiply it back out again to be minus 8 times x plus 2. Take square roots of both sides. So y plus 3 is plus or minus the square root of minus 8 times x plus 2. And then bring the 3 to the other side, and you get y equals minus 3 plus or minus that radical. So there are really 2 equations here, aren't there? One equation is minus 3 plus the square root of that thing, and the other equation is y2, say, minus 3 minus that square root. And those are the 2 equations you would graph on your graphing utility. The first one would give one piece of it, and the second one would give the other piece. Isn't that neat? Okay. Let me ask you some questions now. Let's test ourselves. Suppose I gave you the equation x squared plus the quantity y plus 5 squared equals 16. Let me ask you a question about that. What is it? What's the graph of that? And knowing the graph, identify the key parts. Well, what do you think? It's x squared plus the quantity y plus 5 squared equals 16. What is that? Right, it's a circle. What's the radius? Well, 16 is r squared, so the radius is 4. And where's the center? Well, remember, it's x minus h and then y minus k, so the center is at 0 minus 5, isn't it? That circle is at 0 minus 5. Okay, well, good. We got through circles and parabolas and did some nice examples and drew some pretty pictures. In the next lecture, we'll move on to some more complicated conic sections, ellipses and hyperbolas. Ellipses in particular, I find them very, very interesting to me. They, for instance, the planets move in elliptical orbits around the sun. And ellipses also form, or are the shape of things called whispering galleries, and we'll talk about a whispering gallery next lecture. So I invite you back to continue this study of conic sections. Thank you very much.